Good evening. We're solving this paper. This is like a collection of questions from different exams and different years. So let's get started. So first part, it says, when chlorine gas is bubbled into aqueous potassium iodide, like this equation here, what kind of reaction is this? Now, you just have to keep something in mind that oxidation reduction must occur at the same time. So there's no oxidation without reduction, especially if you have a full equation. I understand if you have a half equation, it might be oxidation reduction, but that's like a full equation. It must be redox. Disproportionation is not likely here because to have this case of redox, you need the same element to be repeated 3 times in the same equation. So it can't be this one either. Cyclohexane dissolves halogens. In the case of iodine, if you put iodine in a funnel like the one I have here, and you let it settle, you're going to have something interesting. You're going to have iodine first dissolving in water, but then it migrates to cyclohexane. Why? Because it dissolves better in cyclohexane. All halogens dissolve much better in organic solvents than the way they dissolve in water. So if you let it settle, you notice that it leaves behind some light brown or yellow color here behind. That's because the majority of it is transferred from the water layer at the bottom to the cyclohexane at the top. And if you just mix it well, or you wait longer, you'll notice that the entire iodine goes into the cyclohexane. Going back to my question, the lower layer is going to be pale yellow. All right? Again, iodine in water, understand, is brown. But in this case, because it has a better option, the iodine just goes to the top layer where it dissolves much better. If you shake, it will be water in one layer, completely transparent, like the one on the right. Okay? Next, it is this question about the reaction of sulfuric acid with halide ions. Now, you need to memorize somehow the products of each halide. When it comes to, once again, iodide and sulfuric acid, you're going to get a whole list of products. Let me show you. Tiny bit, very little hydrogen iodide, which produces misty fumes. Iodine in both forms, solid and gas, some sulfur dioxide, some sulfur, and what makes this reaction distinguishable from all the other halides is the fact that it produces H2S. That's the lowest oxidation state of sulfur, meaning the iodide does the best reduction of sulfur. For that reason, I am picking the last option. So do memorize very well the halides and sulfuric acid. Not the actual equation is not very important. No, the products. Okay? Organic chemistry, which type of reaction occurs when you turn in an alcohol to an alkene? Now, look, reactions of alcohols fall into 2 types. We have oxidation for our syllabus. We have oxidation and we have elimination. Elimination takes place when an alcohol turns into an alkene. That's simply, if you have an alcohol like this, you're going to remove HOH from adjacent carbons and you form an alkene. Another thing you need to memorize is the trends from inorganic chemistry. I mean the trends of thermal stability, trends of, what do you call it? thermal stability and the trend of, it's written here actually, polarizing power of these cations. So in terms of thermal stability, let me remind you of something. When you have a cation next to a polyatomic ion, the smaller the cation, the more highly charged. Think of, for instance, of magnesium versus barium, or magnesium versus potassium, if you like. The smaller the cation, the greater is charge. In other words, you know what I call this? When I have a great charge, small cation, we call this charge density. So the greater the charge density of the cation, the more likely it would polarize the adjacent anion and weakening those covalent bonds. This is carbonate. Carbonate comes with covalent bonds in it. So when you have a small cation next to it, it will break those covalent bonds, makes it weaker, makes it less thermally stable. Why am I talking about this? Because the question here is asking me about these trends, and it happens that all the trends, or all these trends, are reversed. They flip them, with the exception of C. It says the polarizing power of the 2+ ion decreases as you go down. Why does it decrease? Because you go down a group, the ions get bigger and the charge density decreases. Okay? So again, all other options, they wrote the trend, but they reversed it. This is also organic. What's the role of hydroxide when it is reacting with a halogen-alkane? If you have a hydroxide waiting here, okay? What's his role in this reaction? Now, something just to keep in mind, and it saves you a lot of time. The reaction of halogen-alkanes are always described as nucleophilic substitution, right? So any ion reacting with them is always going to be a nucleophile. Sodium chloride dissolves in water, but doesn't dissolve in hexane. Solubility always depends on one thing. It depends on the bonds you have within the solute and the bonds you have in the solvent. Once again, solutes dissolve very well if the bonds you break. What do I mean by broken bonds here? That's not a chemical reaction, just like you're dissolving here, right? The bonds between the solutes themselves and the bonds within the solvent itself are weaker, weaker here, than the new bonds. What do I mean by new bond? A new bond here is a solute solvent, okay? So in my case, they're talking here about solubility of ionic compounds. Ionic compounds dissolve very well in water because this bond I have, we call it dipole ion or ion dipole, is much stronger than the hydrogen bonds you have in water and the ionic bonds you have between the cation and anion. So that's why it dissolves very well in water. Again, you see that bond I have here? It's quite strong. It makes ionic compound dissolve very well in water because it's stronger than existing bonds you have within the ionic compound and within water. So I highlighted the first option here because it is misleading. Many students would just pick this one because it sounds correct. Look, hydrogen bonds between water molecules are stronger than the bonds you have between hexane. But this is not the reason. Actually, if the hydrogen bond is stronger, then the salt won't dissolve. For that reason, I have to pick C because the energy released when the ions are hydrated when I make those hydration shells, when I make the bonds between the iron and the water is stronger than the existing bond, than the bonds between the solutes and the bonds within the water. Okay? This question is about kinetics. What's the best way to define activation energy? So what is activation energy? I think you know this one since you were little. The minimum energy necessary for particles to collide successfully, right? So C is wrong, actually. The minimum energy required to make particles collide. No, it is for successful collision. It is for a collision that will yield a product, okay? Reaction to occur. Because particles collide non-stop, and many of those collisions are not successful because they don't have enough energy. They don't have activation energy. Now, they gave me the energy profile of many diagrams, but this one's quite different because it is for a reversible reaction. Okay? So this is a reversible reaction, and they're giving me the profile of this reaction. Look what they want me to do. They said, find the one where it shows activation energy for a backward reaction when a catalyst is present. Okay? So I'm going product to reaction. Agreed? If it's reversible, this means I am going from the product backward to the reaction. This is perfectly okay for a forward reaction, uncatalyzed. So this is forward and uncatalyzed. This is forward and catalyzed because it reduces activation. This one is backward catalyzed. That's what I'm looking for. And this is backward uncatalyzed. Again, the delta H is always the difference in energy between my reactant, in this case is going to be products because we're going backward, and the top or the highest amount of energy. Okay? So that is delta H. Let me show you where delta H is here. That's delta H. Okay? And this is EA, activation energy. Okay? Number 8, calculation. Which sample will be neutralized with that much acid? So these are the sodium carbonate, the base, reacting with this acid. I just want to find which one matches the same number of moles as it is in the acid. So to start with, I'll find the moles of the acid. Did you notice that this is Cm cubed? So there's no point of me converting dm cubed here while my answers are all Cm cubed. I'm just going to keep it as it is. So in step 1, I'll say 20 times 0.05. That gives me the moles of my acid, right? And then I'll check which one of those options, if I multiply, it gives me the exact same number of moles, okay? So which one of these would actually give me that same number? But we have a little issue here, is that we have different mole ratio, okay? So this is the moles of the acid. I want to find which one of these options gives me the same with the exact mole ratio. So what am I supposed to do about the moles of the acid? I will just half them here because the mole ratio is 2 to 1. So now I need an option that gives me 0.5. Which option gives you 0.5? It's the first one. So during a chemical reaction, reactants must have identical number of moles if they are to completely react. I found the moles of the one. I use the mole ratio and I find which option matches that. Going back to the polarizing power of cations, this said, which one of these has most oxygen when it's been heated? It talks about decomposition of ionic compounds. Do you know that when you decompose something, let's say calcium nitrate, let's say, okay? When that decomposes, it gives me oxygen, it gives me calcium oxide, and it gives me nitrogen dioxide, which is a brown gas. That is group 2 nitrate. Unlike group 1 are more thermally stable. When they decompose, like let's say sodium nitrate, that's only going to give me sodium nitrite and oxygen. So the question here states, which one here is going to perform that way? You just have to pick any member of group 1, pick any member of group 1, with the exception of lithium. Why not lithium? I'm not going to pick lithium because lithium behaves just like group 2 when it comes to its thermal stability. So all decomposition of lithium compounds is going to be just like members of group 2. There is soluble in water, produces steamy acidic fumes, concentrated sulfuric acid. So do you know what they mean by steamy fumes? Steamy fumes is always for something like this: HCl, HBr, HI. Which one of these gives me the highest misty fumes? Is it chloride, bromide, or iodide? It's actually the first one. When it reacts with sulfuric acid, it gives you a lot of HCl. So for me, I'm going to pick chloride, but it's going to be this one, right? Why am I picking the first one? First, because that's the reaction we studied. Second, because AgCl does not react with sulfuric acid. AgCl won't dissolve in the first place to react with sulfuric acid. Why not the first one? It reacts with sulfuric acid, but it's going to give me CO2. It's not what I'm looking for. I'm looking for hydrogen halide. What is the name of this organic molecule? It's in alcohol, right? And let's find the longest chain. It's like CH3, CH, CH3 here, and CH3, right? So based on this, it's the longest chain I have is this, right? So it's propanol, propane 2-ol, and there's a methyl on the second carbon. So it is this one. We have samples of chloropropane, 1-bromopropane that are warmed with water containing silver nitrate. They said the 1-chloropropane reacts more slowly than the propane. So again, why is it that chloroalkanes are slow in their reaction, much slower than bromoalkanes or iodoalkanes? This has to do with what here? This has to do with the strength of the bond. If the bond is stronger, if the bond is shorter, it takes longer to react. So again, short bonds, let me read what I've written here. Long bonds, they require less energy to break, so that makes them react faster. And bromine has a larger radius than chlorine, so that makes it break easily and react faster. Okay? The question after says the reaction of 1-chloropropane with water containing dissolved silver nitrate is what? So reactions of halogenoalkanes, I told you about this one. All of their reactions are nucleophilic substitution with one exception. It is the exception when you dissolve KOH in alcohol. In this case, it's going to be elimination. But nonetheless, all reactions of halogenoalkanes are nucleophilic substitution. Okay? This compound with this formula, it's an amine, can be made by the reaction of alcoholic ammonia with what? So again, which organic groups form amines? It is actually halogenoalkanes, right? Halogenoalkanes, when they react with ammonia, they give you amines. That's another nucleophilic substitution. So I'm going to pick a halogenoalkane, which is this one. The Maxwell-Boltzmann curve comes in every paper. Small questions, not like it's going to be a big topic, but it's helpful to revise here. Look, in the curve, we always have what? We always have the most probable energy. What does that mean? This peak of the curve represents the largest number of particles with this amount of energy. I mean, this tells you what? Tells you that the majority of the particles have energy that is less than the average and far less than activation energy. Average energy is halfway here. So those are the particles that have half energy. These are the most probable energy of particles. And only this section has particles that can react successfully. So X is this one. The molecules with the most common, the largest number of particles with this little amount of energy. Here it says, in an industrial process involving gas reactions producing ammonia, many collisions between particles are unsuccessful. Why is it? Most of the times, particles collide like this. They collide and they have very little amount of energy where they bounce back. Call these elastic collisions. That's not successful. Reason here, because they don't have that minimum amount of energy. They don't have activation energy. The molecular ion in the mass spectrometer, when there is only carbon-12 and hydrogen-1, it's going to be where on the graph? Let me show you this again. This is what do you call it? The mass spectrum of some molecule. Usually the molecular ion, or we call it the parent ion. Let's say if this was methane, okay? This will be 16, okay? You may have a small band of 17 here, maybe. When do you get this? You get if you have some isotope of carbon, which is 13. The question here says, all of my carbon are carbon-12, okay? So where would you find that molecular ion? The molecular ion is going to be the one furthest on the right-hand side, okay? So I'm going to pick this one here, the highest mass. For 18, they're giving me that fragmentation of some molecule where 29, 57, 58, again, we have some molecule being cut into fragments, and we are to identify it. When we took this lesson, I told you to remember what each one of these numbers represent. This one here, it's CH3, CH2. 15 and 14 is 29. Now, let's go down and find which molecule has this particular fragment. You need consecutive CH3, CH2 in those molecules. So where do I have this? I have it here. I have it here, right? Those are not likely to be my answers. How much is the entire molecular mass of this thing? So how much is the biggest fragment I have is 58. The biggest I have is 58. Now, just check which one of these molecules has a total molecular mass of 58. What will you notice? You'll notice that it is only the first one. If you work out the molecular mass of the rest, this and this, it's not. Okay? So again, it's quite common to ask you to distinguish between those two isomers, a ketone and an aldehyde. What do they have in common? Both have the exact same molecular mass. How do you distinguish between them? You'll distinguish by means of their fragmentation. With propanol, it is the only one that has this fragment. Do you know what that 59 represents? That's the one where there is carbon 13, but it's not our case here. Okay. We're done with that first section. We still have another section here. They want me to react barium with water. When you react group 1 or group 2 at the bottom, those react with cold water. Again, take a look at that periodic table. Members of group 1, all of them, and the bottom ones of group 2, like these here, they react with cold water and they produce an alkali. So I'm going to write the equation here, Ba and water gives me barium hydroxide and hydrogen. They want me to include state symbols. So gas, aqueous, liquids, and solid. Balancing it is like this. Okay? Why did I put BaOH2, barium hydroxide, as an aqueous? Because it dissolves. You know, hydroxides of the group 2 are quite soluble. What if I reacted this with an acid, with hydrochloric acid? What would you expect to get? So let me solve this first, and then I return back to this, okay? So I'm going to react this here with an acid, okay? So I'm going to get barium chloride and water, salt and water, acid alkali. And I'll just balance it here. They wanted me to show them redox in this reaction. So how much is the change in the oxidation number of barium here? Barium went from Ba here to its ionic form. So that's a 0 to 2 plus. If something gets oxidized, there's something else must be getting reduced. So what is getting reduced here? The only other species I have here, which is hydrogen. Hydrogen's oxidation number is 1 plus 99% of the time. But here, when it becomes hydrogen gas, how much is this oxidation number is going to be? It's going to turn 0 because this molecule, it's separate. So I'll tell them simply that barium got oxidized while hydrogen is getting reduced. Dilute sulfuric acid is added to another sample, and they said how would the appearance of the product is going to look like. So we have an issue when it comes to barium and sulfate. Barium sulfates are very insoluble. They form a precipitate. That's how we actually test sulfate ions. When I want to identify sulfate, I always add barium. So I'll tell them here, it's going to look white precipitate. Reason, because barium sulfate is insoluble. Okay? Unlike barium chloride. Chlorides are always soluble with the exception of lead and silver. Sulfates are always soluble with the exception of barium. You have two white powders. One is barium carbonate, one is magnesium carbonate. How could you distinguish between those two? By heating. In other words, test the thermal stability of barium carbonate and magnesium carbonate. I told you about this at the beginning. As you go down, the cations are getting bigger. The charge density is decreasing. Thermal stability is always inversely proportional to charge density, meaning those at the top will polarize the anion. They'll weaken its bonds and make it less thermally stable. My magnesium here is going to be less thermally stable than barium at the bottom. So the barium carbonate is thermally stable. Reason, because it would require more heat. How is it going to decompose? How would barium carbonate decompose? Barium carbonate, when it's heated, the oxide and carbon dioxide. Is there another test you can distinguish between the two of them? You can actually distinguish between every two cations by means of their flame tests. So I could try a flame test. Magnesium is no color. Magnesium's flame color is outside our visual spectrum. You can't see its color. So just going to say with magnesium, you're not going to see anything. But barium actually does. Barium's like this color. We call that color pale green color. Now, the organic part, it says what conditions are suitable in terms of temperature when you're reacting sodium hydroxide with halogenoalkanes. So again, I am planning to do what? I want to react chlorobutane with sodium hydroxide one time to make an alkene. Another time, I want to turn it to an alcohol. So again, you have a halogenoalkane. You can do elimination. How? You take NaOH, but it's going to be dissolved into an alcohol. You can always turn a halogenoalkane with the same reagent, but the solvent is different. Here is going to be aqueous. So if I am to turn it to alkene, I'm just going to tell them, make the solvent alcohol. Dissolve that KOH or NaOH in alcohol. This time, the reaction is elimination. What about the other reaction? If I am to turn it to alcohol, it's just change the solvent. There's really no difference in terms of temperature. They want me here to draw the mechanism of this reaction, the nucleophilic substitution. And I'm having 2-chlorobutane. Just gonna put, I like to put that bond between the carbon and the halogen long, so makes it easy for me to draw. It's chlorobutane, meaning that it's chloro, not bromo. Chloro here is going to be in the middle. I'm just going to put the rest of it here. You can make it long with all the carbons, but this way is much easier. Who's my nucleophile here? It is the OH. So I'm just going to put an OH here, negative charge. I'll put the partial positive, partial negative. I'll extend an arrow like this. And then I'll write the product. Cl remains negative here. And the other product is going to be an alcohol. Okay? So this is the nucleophilic substitution. Next, they said we've exposed the alcohol. You've just made 2PCl5. What observation you're going to get? Alcohol and PCl5, you're going to get HCl. Once again, you tell them you're going to get misty fumes, steamy fumes, up to you. They mean the same thing. What about the reaction? Again, I have butanol, so I'm going to write C4H9OH, butanol, plus PCl5. I know I'm getting HCl here, right? I'm going to sub the OH with a Cl. So that's why it's called substitution here. C2H9Cl. How many Cl's am I left with now? I've used one here, one here. I have the P, I have the O, and I have 3 Cl's. So now I write the other product, POCl3. By the way, that's a test. That's how you identify the alcohol group, by the steamy or misty fumes. Oxidation of alcohols. Do you know that primary alcohols, secondary alcohols do get oxidized? Tertiary alcohols never get oxidized. So if you have butane 2-ol, which is secondary, how would you distinguish between this and a tertiary alcohol? Okay? To start with, I'll tell them with secondary alcohol, I am expecting that oxidizing agent to change its color. Potassium dichromate comes in 2 colors, orange as it is. When the redox reaction is over, it's turning green. We're going to tell them this is going to turn from orange to green. But tertiary alcohol is not going to react. Tertiary alcohol, there's no reaction in the first place. Give the structure or formula of an organic compound which forms when this is getting oxidized. So once again, I'll just draw the organic compound here. Butane 2-ol, 2, 3, 4, butane. I have an OH here in the middle. Okay. And I'm going to get this one oxidized. Oxidation is all about what? Oxidation is when oxygen is added and hydrogen is removed. So do you see that hydrogen here at the bottom? Get rid of it. That's oxidation. And Instead of this, I'm going to add an oxygen here. So we get a ketone. Remember, primary alcohols give you aldehydes or carboxylic acids. Secondary, they only give you one product. They only give you ketones. If you're using infrared spectroscopy, could be used to detect whether this has been oxidized. What organic group in this compound will tell you that this product is there? The only organic group that I have here is this. So basically, I will look up inside the infrared spectrometer for a band showing me this ketone group. So I'll tell them I'll be looking for a ketone group because that tells me that the alcohol got oxidized. In chemistry, we have these three intermolecular forces. We have London, we have hydrogen, and we have permanent dipole-dipole. Only one of them increases the strength when you have more electrons. And that's the one, it is London forces, right? They want me to calculate how many electrons are there in CH3F. How many electrons do you have in carbon? Carbon got 6, right? Hydrogen has 1 times 3. Fluorine's atomic number is 9, right? So total here is 18. Now, despite the fact that they both have same number of electrons, meaning London forces is not the problem here. What is making this guy here having higher boiling point than F2? There must be another intermolecular force. What's the other intermolecular force when you have C and F? And please don't tell me hydrogen bond because there's no hydrogen bond. That is permanent dipole, right? I tell them it has a strong intermolecular force, which is a permanent dipole-dipole interaction. Why is it that the HF has the highest among all of them? That's because it has the strongest of intermolecular forces, which is hydrogen bonds. Okay? The last bit of this question, explain why the values of boiling point do not follow the same as these ones. Again, if you take chlorines, you take HCl, it has much lower boiling point than HF. Why? That's because hydrogen bonds only occur if hydrogen is attached to fluorine, attached to bromine, or attached to, what am I saying? Hydrogen bond only exists if attached to fluorine, to nitrogen, or oxygen. Chlorine is not one of these. Now comes the titration question. They're doing that thiosulfate titration. They gave me here the concentration and volume of iodine. They gave me the concentration volume of thiosulfate. To start with, they said, find me the moles of thiosulfate. How do you find it? Moles is concentration times volume. So I'm just going to convert that volume into dm cubed to start with, and I'll multiply. I'll do the same thing now because they're asking me about iodine. I'll do the same thing. Calculate the number of moles of iodine react with this amount of thiosulfate. So you see here, thiosulfate is here, is reacting with iodine. What's the mole ratio I have? It's 2 to 1. So if I am to find how many of those iodines have reacted with the thiosulfate, I would just divide by 2. Again, I did not use the first part here because this is a different reaction. For that question, they only want me to find the moles of iodine reacting with the thiosulfate. So I'm just going to take my previous number and divide by 2. Now they want me to find the moles of iodine from the first equation, which is those ones here. So I'll 50 over 1,000 multiplied by concentration. Now, this is the iodine that was reacting with that tin. The remaining iodine, look what they said. They said the excess iodine was reacted with thiosulfate. So here I have a greater moles of iodine initially, and here I have less moles of iodine because I only have the excess iodine reacting here, right? The question is asking me, use your answers to calculate the number of iodine that was reacted with tin. I repeat, you had that much iodine to start with, some reacted with tin, okay? And the leftover, so let's say that much reacted with tin, the remaining parts, let's make it here, the remaining part did not react with tin. What did we do with that remaining part? That remaining part, we reacted with thiosulfate. If I am to find the part that reacted with the tin, which is the first part, I take the total, which is this answer, and I minus the one that reacted with thiosulfate. This gives me how much of the iodine reacting with tin. So I'm just going to subtract those two previous numbers. Okay? Now, let's check the ratio between iodine and tin in the first reaction. They have identical ratios. So whatever number of moles I have here is going to be the same as the number of moles of tin. The last question here, or before the last, they said, find me how much tin there is in the original sample. So that's the mass of my sample of tin. If I could just find the mass of tin that reacted, I could take this as a percentage from the original mass. Right? So again, initially we had a rock, which is this mass. We wanted to find how much of this rock has tin in it. We reacted it with iodine. Now I know the moles of tin in this sample. So I could just find the mass. I'll multiply the moles of iodine, which is same as tin, with the molecular mass or the atomic mass of tin. This comes from the periodic table, tin, Sn, okay? And I get the mass. Now I want to find this mass as a percentage of the original. So I divide by 10.25 times 100. If somebody asked you about reliability, reliability always has to do with what? Always has to do with repeats. You repeat to make it more reliable. So if I want to improve the reliability of step 4, what am I supposed to do? I tell them you must have repeated it. But how am I supposed to repeat? Because if I just repeat as it is, it's not going to be helpful. I divide my solution into 4 portions or so. just multiples, and I do separate titrations. Once again, let's check step 4. Step 4 is the one where we did the titration. They did this titration one time. Titration is never done once. You must do it several times because it's very likely that you make an error. So usually, if I am to do several titrations, I divide my solution several times, and this way I do several titrations. If there is any error, I eliminate that. Each time the burette was red, it gave me that much error. Calculate the percentage error if your measurement value is that much. So again, if you are to find percentage error, it is the uncertainty divided by the volume you're measuring. You just have to check with the tools because they said the question, check. They said each time. How many times you read a burette when you're doing a measurement? You read the initial volume and then you read the other volume. So I'm going to do that mistake, the error, I'm going to do it twice. So I take that uncertainty, I multiply by 2, and I divide by the volume. How do you reduce percentage error? It's a percentage. How do I decrease that percentage error? By keeping the same burette. If you go back to that same formula I was showing you there, this is fixed. Why? Because it's the same burette. Okay? What's the only thing I can change in this formula and I reduce the percentage? It is the volume. If I increase the volume I'm measuring, I will always reduce the percentage error. How do I increase the volume? It's not me who decides how much volume I'm using in the burette. Look, if this was your burette here, and this is my solution, the one I'm titrating, I can always increase here. I reduce that concentration of it. When I reduce this concentration, this means what? What's going to happen to every time I'm pouring from my burette? So the concentration of my titer here is less, I should say. Then you're going to increase the volume of the solution you're pouring from your burette. So the greater the volume that I'm measuring, the lower the percentage error. And the best way to do it is to use less concentration of your titer in your burette, because that means you're going to be pouring more and more of this solution. Sometimes you don't need an indicator when you're doing titration. That is when the solutions you're using have specific colors. In my case here, because I am dealing with iodine and I did not add any indicator, what would be the color near the end of titration or the end point of this titration without using indicator? Look, with the sodium thiosulfate titration, when I'm titrating iodide, initially that's the color. That's the color of iodine in water. You add the thiosulfate, it goes light and light and light and light, until it becomes very pale. We call this color stroke color. Okay? At this point, because it's so difficult to tell when's the end point, we usually add starch. And that helps me to find the end point easily, because that starch reacts with the iodine and tells me there is still some iodine. Okay? But without that starch, what do you expect to happen? Without it, the color is going to be stroke color or very pale yellow. Now comes the energetics question. And what's this about? This is about combustion of methanol. They want me to find delta H of this combustion. Nicely, they gave me the mass of water, but usually they put it like this. They put cm cubed of water, and you have to realize that 75 cm cubed of water is 75 grams. But this time is more straightforward. So I'm going to write Q equals to the mass times C, specific heat capacity, times delta T. So this will help me to find the energy released in this reaction. That is Q, which is again the mass, delta T, and specific heat capacity. It's always in joules. Step 2, I'm going to convert this to kilojoules. I divide by 1,000. And then I divide by the number of moles of methanol. So to find the number of moles of methanol, I'll divide this mass over its molecular mass. Because delta H is what? Delta H is the Q I just found divided by the moles of the methanol. So step 2, I'll just convert this to kilojoules. Then I'll find the moles of methanol. That's its molecular mass. And I'll divide those kilojoules over the number of moles. I get delta H. Now, also, they may not even tell you to include the sign. You must include a sign. How do I know whether the delta H is positive or negative? Combustion is exothermic, so it must be negative, right? If you're confused, when you find that the temperature is rising, that's always negative sign. That's always delta H is exothermic. Okay? So this is delta H of the combustion of methanol. Next, they gave me 2 reactions at equilibrium, like the ones I have here. And they said, explain the effect of increasing pressure on the yield and rate of this reaction. Let's talk pressure first. You increase pressure on the yield, you will always go to the side that has fewer moles of gas. So how many moles of gas do I have here? These are 2. How many moles of gas here? 4. So if I increase the pressure, I will take equilibrium to the side on the left. That means what? That means your yield, which is always referring to the product, is going to decrease. Increase of pressure and rate of reaction is always going to increase the rate. Because if you pressurize particles, then they come close and they're more likely to collide. So I'll tell them here, pressure and yield is going to decrease because equilibrium is shifting left-hand side. Increase in pressure increases the rate because less volume, fewer space between the particles, then they're more likely to collide. Speaking now of step 2, explain why 500 kelvins is a compromise for step 2 of this reaction. Why don't we use any higher, any lower? Look, this reaction is exothermic. This is an issue we always face when there is an exothermic reaction. With exothermic reaction, we have a dilemma, an issue. I can't increase temperature because an increase of temperature will take equilibrium backwards. How do I know? That's exothermic. This delta H they put on the right is always referring to the forward reaction. So I can't really increase temperature. And I can't decrease temperature. You know why I can't decrease temperature? Because less temperature, the reaction is slow. So we usually put a moderate, optimum, halfway temperature, like the one I have here. This will give me enough rate, and it's not high enough to favor the backward reaction. Because High temperatures favor endothermic reaction. In my case, it's the backward reaction. So low temperature would be slower. So this is a compromise, an optimum for yield. Yield is good enough, and the rate is also reasonable. Okay. Next, we're having the usual Hess's cycle. So let's move on. That's my reaction. That's delta H of this reaction. They gave me enthalpy of combustion of carbon monoxide and hydrogen, and they wanted me to calculate the delta H for the combustion of this guy. I'm looking for this, okay? What do I have? I have the combustion of carbon monoxide, and I have the combustion of hydrogen, all being given. What are the products of combustion? Products of combustion are carbon dioxide and hydrogen, and water, I should say. Okay? Now, let's write small, like, formula. So we apply that formula here. So I'm going to say, let's call this delta H1. And let's call it X, Y, and Z is way easier, right? So I'm going to call this X, Y, Z, and cube. Okay? So X equals what? X equals to Y plus Z. Why? Because all of these arrows are going this direction, right? All of them are going that way. Q is in the opposite direction. So minus Q. If I'm looking now for Q, what would be Q? Q is going to be Y plus Z minus X, okay? All it takes now is to sub these numbers with their values. So carbon monoxide is going to be negative 2A3, negative 2A3. And I have 2 of the hydrogen plus 2 times negative 286. Okay? That's the Z, I call it for hydrogen. And X is given here, right? Minus negative 91. So how much is this delta H's value? Is going to be negative 6.4. Okay? Is this clear? So I just check the direction of the arrows and I sub the values, and keep in mind whenever they have coefficient like this goes with your calculation too. Okay, now comes the last question, which is this one. They said this is the concentration of bromine, and they said prove to me that this number for bromine is greater than this number in ppm. Let me remind you what the ppm stands for. ppm is the mass of the solute, bromine, mass of the solvent, which is the water, times million. So it's going to be what? It's going to be that 60 here, okay? And I have the solvent. They said here, look at it. They said it is 1 dm cubed. So I'm just going to put 1,000 grams times 10 to the power 6. And I am looking for the mass of my bromine here. So based on this, M equals what? M is going to be 60 times 1,000 divided by a million, right? So if I work out this calculation, this one was 2.2 grams, right? Because it's 1 dm cubed. Mine here is going to be what? Mine is going to be, this goes with this. So 60 over 1,000, that's 0.06. Okay? It's going to write it here, 60 times 1,000 divided by a million. So this number, based on what I've just done here, this number is is lower than the mass I have here. Write an ionic equation for the reaction of chlorine with bromide. Include state symbols. So chlorine is a stronger oxidizing agent than bromide. So it's going to get Cl minus plus Br2. State symbols, chlorine in water. So again, this is chlorine gas. I'll write it this way. Bromide is aqueous, and bromine in water. Okay? It's written here for you, by the way, bromine. Here it says, what would be observed in this reaction? What's the color before? And what's the color after? Before, it's colorless, right? Chlorine in water is colorless. We know that. Chlorine gas is pale green. When you dissolve it in water, it's colorless. Bromine in water is orange. Bromine, as it is brown. In water is orange. Why the addition of an acid to this equilibrium prevent further hydrolysis of bromine? So go back to the first reaction here. What do acids provide you with? Acids provide you with this H+. Okay? So if I add extra amount of a product, how would you expect equilibrium to go? More product will shift equilibrium to the reactant side. And that will prevent the hydrolysis of bromine. It will prevent the reaction of bromine and water. So I'll tell them this one here. Tell them like addition of acid increases concentration of H+, a reactant. Therefore, this hydrolysis is not going to happen. It's going to shift equilibrium to the left-hand side. Once again, if you increase reactant, you favor the forward reaction. But if you increase a product, you will decrease, or you favor the backward reaction, I should say. Okay? Here it says, assuming the hydrolysis of bromine is endothermic, how an increase of temperature would affect the equilibrium. So here, going back, delta H is positive, okay? The forward reaction is endothermic. If I increase temperature, which way will always favor equilibrium? Heat always favor the endothermic reaction. How I always remember it. Heat, endo, okay? So if I increase temperature, this will shift equilibrium forward towards the endothermic reaction, and it will increase the reaction of bromine and water. Again, why high temperatures favor endothermic reactions? Because you're disturbing equilibrium. When you disturb equilibrium, you would always allow equilibrium to react to you. You increase temperature, equilibrium will respond by absorbing that heat you've supplied. And the way you would absorb heat is endothermic. Activation age, explain why an increase in temperature increases rate. Easy, this one, right? Increased temperature, particles have more kinetic. They have energy greater than EA, activation, allowing more successful collisions. Now, this reaction is disproportionation, where bromine goes to -1. That's a zero, right? It's a separate neutral. That's -1. How much is the oxidation number of bromine here? It is Br plus -2, that's the oxygen, equals to -1. So Br is what then? The Br's oxidation number is going to be +1, right? So that's why it is disproportionation, because it decreases oxidation number and increased it at the same time. More about equilibrium here. What do I have? I said define equilibrium, right? Two features of any system at equilibrium. To be at equilibrium, you first have to have the rate of the forward and backward reactions equal. Okay? Second feature, the concentrations of reactants and products must be, you don't say equal here, you say constant. Concentrations are constant. The last bit says explain how an increase in concentration of carbonate, where is carbonate here, a reactant, affects the amount of CO2. In other words, how is it going to affect the amount of CO2? If I increase this, the CO2 is going to decrease. Do you know why? Because you increase concentration of reactant, equilibrium shifts forward, trying to decrease that reactant, and that will eat through, that will reduce the concentration or the volume of CO2. So I'll tell them here, carbonate increases, equilibrium shifts to the right, and meanwhile, the reactants as a whole will decrease. Okay? Okay, now your exam is Monday. We're going to meet again for one last revision on Sunday. We're going to do one last online revision on Sunday before your Monday's exam. I will now let you go, unless you have any question.